This is the second video in my series on causal inference, and this one is focusing on individual level causal inference. So, as always, I need to acknowledge this book, What If, by Miguel Hernan and James Robbins, which is where I got most of these ideas and the order in which I'm presenting them. So this is kind of an informal hierarchy of causal inference, and at the top here we have the potential outcomes framework, which is a very kind of hypothetical look at causal inference, but is the actual if you think about how you use causal inference in your daily life, is like the definition of cause. The next best thing we have below is experimental lab-based, and then experimental randomized controlled trials, bringing it out of the lab and into the real world. And below that we have analytical observational, that's like cross-sectional, cohort, and case control. And below that we have descriptive observational, which is just looking at like the prevalence or a case study or something like that. So I think there's many like pyramids of causal inference out there, and this is just my take on it, basically. And this is going to kind of guide the flow of some of the videos, too. So as we talked about last time, a causal relationship is really any exposure or treatment enacting a causal effect on an outcome. So a common one is smoking leading to an increased prevalence of lung cancer or an increased risk of lung cancer. But there's also things like the flu leading to a decreased likelihood of getting, the flu vaccine leading to a decreased likelihood of getting the flu. So that kind of brings us to the idea that a causal relationship is anything that leads to a change in another variable, and that can increase or decrease it. So this is the example I used last time. The idea of individual level causal inference is kind of encompassed in this statement, and I'm saying Pete just so we know it's like at an individual level. Pete is saying, I would have gotten the flu if it wasn't for that vaccine. So Pete is 100% attributing his lack of flu to the fact that he got the vaccine, and is saying that if I hadn't got the vaccine, I would have gotten the flu. So basically what that looks like, we have this timeline one where Pete got the vaccine and he didn't get the outcome. If we were able to go back in time and play out that exact same course of events, except in timeline 2, Pete doesn't get the vaccine, and if we see that he got sick, that is a complete replication of the course of events. Timeline 1 and timeline 2 are identical, except for the fact that Pete got the vaccine in timeline 1 and didn't in timeline 2. So we can attribute any difference in the flu to that change in exposure. So this would be 100% individual level causal inference that an individual, this individual Pete didn't get the flu because he got the vaccine. So this is basically like how we use causal inference in a daily basis, as we make statements like that. Like, this wouldn't have happened if it wasn't for X, and that's not something we can actually observe, and that's why it's mostly hypothetical. But as soon as we get some notation formally describing these concepts, all of a sudden it becomes more amenable to statistical analysis, and that's the direction I'm going, because when you consider it just at this level where it's just looking at in timeline 1 and timeline 2, like obviously, like why is it worth thinking about if only one of these timelines is observable? But you'll see as soon as we're able to apply notation to it, it becomes a little more amenable to actual analysis, like marginal structural models and inverse probability of treatment weighting, but that's going to come up in later videos. So now we have our notation. So I know I've been saying like X for an exposure kind of informally, but from now on I'm going to refer to the exposure or treatment as A. And the situation where someone is treated or is exposure positive, that would be A equals 1, and A equals 0 for when they're not. The outcome will remain as Y, and Y equals 1 will be outcome positive. I think the example I am like commonly using going forward is things like mortality or getting the flu. So Y equals 1 would be dying or getting the flu, and Y equals 0 would be if someone didn't get the flu or didn't die. So just kind of linking this notation to back to our example with Pete. So this Y subscript A equals 1, you'll notice it went from being capital to lowercase. Capital is it like kind of conceptually, where lowercase is what's actually happening in the context of like the statement you're writing. Sorry, that was a bit hard to explain, but you'll see. So Y subscript A equals 1 is someone's outcome status when they were treated. So in y a equals 1, we have Pete has this observed state of getting the vaccine and then not getting the flu. So y subscript a equals 1 is equal to 0, and that is shorthand. This thing to the right here is shorthand for the outcome when Pete was vaccinated or was exposed is 0. And now you have this other situation. What is Pete's outcome when he was untreated or unexposed? So y subscript a equals 0. This is the counterfactual outcome because we only observed that top one. But if we were to go back in time, this counterfactual situation where this individual wasn't treated, they got the flu. So y subscript a equals 0 is equal to 1 because that shorthand for the outcome status when this individual wasn't treated is 1. So now we can have like a formal notation for when there's a causal effect. So when the outcome when an individual is treated doesn't equal their outcome when an individual is untreated, that's the definition of a causal effect at the individual level. This subscript a equals 1 y is not equal to the subscript a equals 0 y. So now we can apply that to I find it very helpful to link that with visuals. So again, we have our observed state, getting the vaccine and not getting the outcome. So that is y equals 0 among the a equals 1 state. And in the a equals 0 state below, we have it equaling 1. So we can see that 1 and 0 are not equal, so that's the definition of a causal effect. This vaccine was protective in this individual. There's a lot of times that there's an absence of a causal effect, so there's two ways that can occur here. Either this is a situation where the outcome is 0, regardless of whether they got the vaccine or not. So this individual was not helped by the vaccine because they weren't going to get the flu, whether they got the vaccine or not. This is an example of someone who got sick regardless of whether they got the vaccine or not. And in both these situations, the y status when a equals 1 and the y status when a equals 0 is equal. So there's no causal effect. So that leads us to this concept of potential outcomes. So for each combination of exposure and outcome, when there's like two exposure groups and two outcome types, so getting the vaccine and not getting the vaccine, or getting sick or not getting sick, that leads to 4 combinations of exposure and outcome, and each individual will only have one observed thing that is occurring. Each individual either gets the vaccine or they don't, and they either get sick or they don't. So basically, only one of these 4 things is observed, but we're able to apply this to notation that's going to come up in later lectures that'll allow us to basically make assumptions about what's happening at the other levels of the counterfactual levels, basically. And what is making this the perfect level of causal inference? Like you'll remember, like I had it at the in the Minecraft thing. It was the diamond pickaxe. So why that's the most valuable one is because so much is held constant between these two situations. So Pete got the vaccine and didn't get the outcome. And we went back in time, so the fact that we're playing out these events over the same calendar time, like over this, like from like September 1st to whatever, like we're controlling for everything that occurred as a function of like calendar time and geography. So if Pete lives in Toronto, we've controlled for whatever's happening in Toronto from like September 1st to September 10th or whenever this is happening. And we've also controlled any individual factors that are strictly related to Pete, such as his age, sex, and just various like history of the flu. So much is identical between timeline 1 and timeline 2 that any difference in outcome can be attributed to any difference in exposure. So just kind of visualizing that in a Venn diagram. In timeline 1 and timeline 2, things that make them different are he's vaccinated in timeline 1 and unvaccinated in timeline 2. But so many things are shared by the two timelines, and that leads to this idea of exchangeability. So exchangeability is a group level phenomenon that's going to come up later, but it's basically the idea that the two groups or the two timelines basically are so identical that they can be considered exchangeable, where they just are the same in every way except the treatment status. And then this is applied to a group level here, where we, instead of before, when we had Pete and his treated at the top and untreated at the bottom state, we have one individual in our treated group and one individual in our non-treated group, and they're the same individual. Everything we do in real, like, applied epidemiology, comparing one group to another, is just trying to simulate that. If we could have, like, clones of the same individual in the treated and untreated group, that would be great, but basically we need to try and have them as similar as possible in distribution of all these confounders, like age and sex and stuff. So basically, each of these individuals in the treated group will be vaccinated, and in the untreated group, everyone won't be vaccinated, and then you have this distribution of people in each group that get the outcome. And you look at, I guess, just in an informal way, in the untreated group, you can see more people are coughing, so you can see there more of them got the outcome, and that would be some group level evidence that the vaccine is preventing the outcome a bit. But yeah, I'm going to expand on this in the next video that's going to talk about group level causal inference, and yeah, I hope that didn't get too confusing. So, yeah, sorry, I guess that's kind of what I was talking about there, where in the one group, in the treated group, there's a lot of reasons they might be different than the untreated group. It's not the same as comparing them to themselves, so there's some exchangeability issues if we don't do this carefully. For those who decide to get treated, basically might be of higher socioeconomic status. They might just have a bunch of traits that are involved with their decision to get vaccinated. And that could lead to these two groups not being comparable. And all of a sudden, if one group gets sick a lot more often, it's hard to say whether that's because they got vaccinated or not.